this video we will learn about the basics of signal processing. This signal processing will be done some part by the RTL, by the radio, and the other part will be done by us with the MATLAB software in our PC. So, in this chapter we will learn the fundamentals about 4 techniques basic in this domain. The first one is going from time domain to frequency domain, and the way back, of course. The second one is a very good application, that's the filters. The third one is the analog to digital conversion, and the fourth one is the digital to analog conversion. Some of this processing will be done in the digital domain, and the other part will be done in the analog domain. The first one, to go from the time domain to the frequency domain, we will need to do a transform. This transform is the one that you have here. This, the uppercase X, means that it belongs to the frequency domain, and the lowercase x means that you are in the time domain. Also, the F and the T helps you to know in which domain you are. So, if you have a signal, for example, a cosine, and you want to calculate the Fourier transform of this cosine, you only have to multiply the cosine with this signal and to calculate the integral. And you will have the Fourier transform of this cosine. Also, if you want to do it back, to go from the frequency domain to the time domain, you will have to do this operation. Please note that here you have a minus signal and here you don't. These are 5 good properties of the Fourier transform. For the purpose of this course, the most important one is the 4th one. The convolution in time, it's a product in frequency. So when you introduce a signal into a system, you are doing the convolution of this signal with the time response of the system. In the frequency domain, you will only need to multiply one by the other. These are the most useful transform pairs. Please let me introduce first the 2 of the more common signals in this domain. This is the unit impulse, or also called the Dirac delta. It's a signal which value it's always zero, but on 0 its value is 1. And the unit step, it's a signal that has infinite values of 0 from minus infinite to 0, and then when t equals to 0 comes to 1. So here it's 1. Also, the Dirac delta is the derivative in time of the unit step. Going back to the transform pairs, the Dirac delta, the transform of the Dirac delta, it's 1, a constant. And also the transform of 1, it's a Dirac delta in frequency. The transform of a cosine will be 2 impulses, one centered in f0 and the other one in minus f0. And also, very important when we talk about sampling, the transform of a train of impulses will be, a train of impulses in time will be a train of impulses in frequency. What we have said before applies to analog signal, to continuous analog signals. But in discrete time, this is not continuous domain. Discrete means that we will have signals that are sampled, so we will only have values at certain moments. In this domain, we won't work with the Fourier transform as we know it. We will work with the discrete Fourier transform. but actually we won't work with the DFT. We will use an optimization of this transform called FFT. FFT means fast Fourier transform. So here this optimization means faster. This is the expression for the FFT. These are the time domain samples, and these are the frequency domain samples. And this part is the same as we have in the Fourier transform, but now we don't have an integral, we have a sum. Here we can see the FFT at work. This signal in the left, it's the sum of 3 tones added, one at 50 Hz, the other one at 100 Hz, and the third one at 400 Hz. So if we perform this FFT, we can see that there are 3 tones, one at 50 Hz, the other one at 100 Hz, and the third one at 400 Hz. This is done by a very simple MATLAB command, the FFT. You only need to tell MATLAB the signal that you want to perform the FFT with, and the number of samples that you want. In this case, the number of samples was 1024. This 1024 is this n here. Filtering. Once we are comfortable with Fourier transforms and going from time domain to frequency domain, we can do some filtering. This filtering means letting some frequencies pass through the system, through the filter, and the other frequencies don't. There are 3 types of filter. The first one is the low-pass filter, which lets pass the frequencies between 0 and the highest frequency of the filter, the cutoff frequency. The second one is the bandpass filter, which lowest frequency is more than 0 and also has a higher cutoff frequency. And finally, the high pass filter, which is more or less ideal because you can have a filter with infinite frequency as infinite hertz as a frequency cutoff, but ideally it's a filter that does not pass these frequencies here and lets pass these frequencies here. Another very important algorithm that should be understood is the analog to digital conversion. You start from an analog signal here, and you want to have a set of ones and zeros. That's it, a digital signal. So this process is done in 3 steps. The first one, it's the sampling. You take samples of this analog signal at a certain pace, at a certain rate. In this case, we will call this rate Fs, which is also the inverse of the sampling period, Ts. When we have this function sampled, you will want to quantizate it. What does it mean? Reducing the possible values of this signal to the infinite possible values of this signal to a finite set of values. And then you will assign to each of these possible values, you will assign a number. And this number will be formed by ones and zeros. Let's look into it into more detail. First of all, the sampling. We take a sample at a constant rate. This means one sample each 1 by Fs seconds, or one sample each Ts seconds. In time domain, you are multiplying the signal that you want to sample by a train of impulses. So you will have your analog signal, you multiply by a train of impulses separated by the sampling period, and you will have the sampled signal. In frequency domain, as we saw before, the Fourier transform of a train of impulses will be a train of impulses in the frequency domain. So if you convolute this signal, the signal that you want to sample, with the train of impulses in the frequency domain, you will have a lot of copies of this signal separated by Fs, the sampling frequency. So this leads us to an important result. If you want to recover the signal after that sampling, which is something desirable, you will need to take samples at a rate that needs to be at least twice the maximum frequency of the signal to be sampled. So let's look here. If you have a signal which bandwidth, which maximum frequency is W, you will need to take samples at a sampling rate higher than 2W. This is also called the Nyquist theorem. Let's move on. The quantization. Once we have sampled the signal, it also can take infinite values. For example, this could be 1, this could be 0.83, and so on. So now we will need to reduce these infinite possibilities into a finite set of values. So we will work with something very similar to a ladder. So every signal that comes from here, its input comes from here to here, will be assigned to this step here. So it will be quantized. A range of infinite possible values at the input are assigned to a finite set of values at the output. Each value at the output will be called step. Of course, having small steps will lead to a more need of bits than having a large step. So you will have more resolution with smaller steps, or less resolution with bigger steps. And finally, the codification. The codification means assigning a numerical value to each step. So for example, if we have 8 steps here for all the possible values, infinite in theory, values at the input, we will have 8 possible values at the output. And if we have 8 possible values, you will need 3 bytes to codify all of them. If we want to go, we have digitized the signal. We move from analog to digital, and now we want to do the opposite, to reconstruct the analog signal going from the digital one. So we have a bit stream. We will need to find the analog signal. Going back to the Nyquist theorem, if you have a signal here and you have sampled it, so now its spectrum is periodical. What you will need to do is to filter this signal. This is the mask of the spectrum. You will only take this part, so you will have this. But, and look, notice that the cutoff frequency of this filter is the sampling frequency, the half of the sampling frequency. But if you take samples with a sampling frequency below twice the bandwidth of the signal, you will lose information. You can draw a sketch of this, of the picture in the left, changing these values, having a larger filter here, or having also a signal with a higher bandwidth here, and you can think about the consequences. But the most important thing is that if you take samples at this rate, twice or more times the bandwidth of the signal, you will be able to reconstruct the signal without losses. In this chapter, we have seen how to transform time signals into the frequency domain and also the way back. In the frequency domain, we introduced the filters, a very intuitive application and very useful in communications once we understand the Fourier transforms. And also we have seen how to digitize analog signals and also how to reconstruct them. Thank you very much for your attention.